Extremely important quantity that we want to compute is the temperature power spectrum, T as a function of multiple L. Why is it so important? Because it's a quantity that we can both predict theoretically and compare to observations. And to compute it, we just need to perform one integral over Fourier wave number with two terms in the integrand. The primordial spectrum. The primordial spectrum should be either computed from inflation, or we can use just a prescription. And to make our life simple, we will just take a power law, which is a simple prediction from inflation with just an amplitude and a tilt. And then we still have to work in order to compute the photon transfer function theta of temperature anisotropies for multiple L today for a wave number k. And today we are going to put all our efforts on trying to understand what this quantity looks like, and then use this formula to understand the shape of the CL spectrum. And so we started a bit, and we say that to avoid integrating this complicated hierarchy of Boltzmann equations, we will use a formal solution of Zaldariaga and Harari, which gives the multiple that we want to compute as an integral over three terms. And in each three term, you have this function of time, this perturbation, and this spherical Bessel function, which says that each of these terms account for a physical effect relevant at the time described by the green function and projected from Fourier to multiple space through the spherical Bessel functions. And we had time to explain this projection, how the projection works. So now we will go through the terms one by one, and we start with the first line. In the first line, we have here the visibility function. For simplicity, we will neglect rayonization, and so we will consider that this function is very peaked around the time of photon decoupling, recombination. And so the first effect is an effect taking place at decoupling on the last scattering surface. And then because the integrand is non-zero only when eta is equal to eta of decoupling, it means that the projection will always be done by this function evaluated at eta equal eta dec. And so this function will be non-zero only when L is close to k times eta 0 minus eta dec. And this gives a one-to-one correspondence between a multiple and a mode. A wave number k will contribute to the spectrum at a given multiple defined through this relation. Now, what is the physical effect? It comes from theta 0 plus psi, which then is supposed to be evaluated close to the time of decoupling for a given Fourier mode k. The first term is the obvious one. It just says that if we have a temperature fluctuation on the last scattering surface, we are going to see it today on the CMB map. You can imagine that this is a portion of the last scattering sphere. The last scattering sphere would then take a big space. We are the observer, and we look at the sphere, and if the photon here acquired a higher or smaller temperature, we will see this also as a temperature fluctuation. So if we had only this term, it would say, okay, the value of theta on the last scattering surface contributes directly to our map. Super intuitive. What is more interesting is that there are additional terms and effects. And this term psi accounts for a gravitational Doppler shift. Because on the last scattering surface, if we have hot points and cold spots, hot spots and cold spots, it means that we have over densities and under densities. And thus, we also have gravitational potential wells or maxima. And the photon need to leave these potential wells or maxima, and this will either make them lose some momentum or gain some momentum. So schematically here, I look at a photon coming from this hot region, and so when it leaves the last scattering surface, it's hotter than the average. But in this overdensity, there is a gravitational potential well, and it needs to climb out of it, losing energy and becoming colder, which is why I turned the line into a blue line. This photon comes from an underdensity. And underdensity is a maximum of the potential, gravitational potential. And while leaving this maximum, it will gain momentum and become hotter. And you could wonder which of the two terms wins. Is it the overdensity? Is it the gravitational Doppler shift? It's a very nice question. The answer is not so trivial because it depends on which scale you consider, which value of k. But let me assume that I look at very small values of k, so very large wavelengths. Then on very large wavelengths, we are in the super Hubble regime. We can apply the adiabatic initial condition that we studied yesterday. And if you come back to this relation, you find that they tell you that psi is equal to -2 theta 0 on super Hubble scales, which means that in absolute values, these terms wins. And so this term is going to return completely the situation. The hot photon will become a cold one, the cold photon will become a hot one. And so on large scales, we will get a negative image of the CMB. What appears as a blue or cold region is in fact an overdensity and vice versa. But this is true only for large scales. For small scales, psi becomes negligible, as we will explain later. And so on small scales, we have a positive image of the CMB. And so this is the first term. It's called Sachs-Wolf because the fact that the anisotropy we see are the intrinsic anisotropies on the last scattering surface corrected by this gravitational Doppler shift effect was found by two cosmologists, Sachs and Wolf, very early, I think in the late 60s. It's called the Sachs-Wolf formula, and this combination of terms is called the Sachs-Wolf term. And it's a dominant effect in CMB physics. But now we have other terms. And the second term is the second line. Yes? Yeah, we will clarify this later on. We will see we have a range of scales to consider. And here we are evaluating our fluctuation at the time of decoupling. There will be some plots summarizing all this later on. And we will see that in the range of scales that we can observe at decoupling, the smallest value of observable modes are still super Hubble, and the largest values of k that we can observe are sub-Hubble. We will see that the Hubble radius at decoupling is in the middle of the range of scales that we can observe. So this will clarify later. Good. Second term. The second term contains theta b. I remind you, this is a divergence of the bulk velocity of the photons. We have again this visibility function. So we are again filtering an effect that takes place precisely at the time of recombination, and that will be projected according to the same relation into multiple space. There is a prime here which appears when you do the algebra, because there is a gradient in this term at some point. It generates a derivative here that's not important for us. Sometimes you see a version of this integral where people have used the integration by parts, such that the derivative has moved from the blue term to the red term. This is a technical detail, I won't comment on it. Okay, why do we have a bulk velocity of photons here? It comes from, okay, theta b is really related to Vb, the bulk velocity of the photon, at least the component of the bulk velocity which belongs to Bardeen scalars. Since theta b is a divergence of Vb, you expect that Vb in Fourier space is theta b over k. And this term has to do with the fact that the photons here were in thermal equilibrium with the baryons, forming a fluid with really bulk velocities. And for instance, you can expect that the fluid was falling towards hot regions over densities and escaping from undense regions. And so the photons we see on the last scattering surface are like ejected with an initial bulk velocity that will cause a normal Doppler shift. Not the gravitational Doppler shift, the usual Doppler shift coming from velocities and from the projection of this bulk velocity on the line of sight, such that the photon here, if they were moving to the left, it's just an example, seem to have a smaller wavelength to us, so they seem to be redshifted by the Doppler shift, and vice versa for these photons whose bulk velocity is pointing towards us. So this is a correction to the first effect. We will see that, yes. So the connection between the over and under density and the bulk velocity is complicated. It's not always the case that in a blue region the velocity is oriented to the right and in the red region to the left. This is a random. I just picked up a random example. Yeah. So the bulk velocity in this point depends on the distribution of matter around. It will always point to the direction where the most matter is concentrated. So the Doppler effect is correlated to the effect of intrinsic anisotropies, because it's true that if you are close to a hot spot, you will be attracted towards the hot spot, but you don't know if the center of the hot spot is on the left or on the right. So these bulk velocities still have a kind of random distribution, not so much correlated to the patterns on the last scattering surface. So it's a non-trivial combination of the two effects. All right, this is the Doppler term. We will see later that it's significant. And now the last line is also very interesting. And in the last line, we see that our integrand starts not with a visibility function, but the exponential of minus the optical depth. If we compute the optical depth before decoupling, we have seen that it's huge. Cosmic fog is thick. And so exponential minus tau is essentially 0. If we compute the optical depth after recombination, tau is small. The cosmic fog is not thick at all. And so this is, in this case, almost like a factor 1. So this factor is telling us that this effect is 0 before decoupling, but essentially 1 after decoupling. And so in the integral, we will get a contribution of this term for all times integrated along the line of sight of the photon from decoupling until today. And so for this effect, there is not a single one-to-one correspondence between Fourier modes and times. Because when we will look at the effect of the red function at a given time eta between decoupling and today, then we will have to project with this value of eta. And so the same mode will contribute to different multiples because we will see this mode at different times eta. Like if we had an infinity of spheres on which we observe our Fourier modes. And when we consider the effect of this function at late times close to us, they are close to us, so just by trigonometry, a given wavelength appears under a large angle, that means a small multiple L. So the projection effect then is not so trivial. So this term is a partial derivative of phi m psi along the line of sight. It's really a partial and not a total derivative, which means that we cannot integrate it analytically. And it comes from what we called yesterday the dilation and the Doppler shift effect, but along the line of sight of the photons. The photons are leaving the last scattering surface, and while they are traveling to us, they constantly go through maxima and minima of the gravitational potential, and so they continuously get redshifted, blue shifted, redshifted, blue shifted. The remarkable thing is that when these metric fluctuations are static, I don't say when they vanish, I say when they are complicated but static, then the partial derivative vanishes, because you can show that in this case the effect is a conservative effect. Any blue shifting is compensated by a red shifting, and what matters is only the comparison of the gravitational potential at emission and at reception. And then this effect only depends on the difference between psi or phi on the last scattering surface and at the location of the observer. This term psi on the last scattering surface is a term that we already accounted for with the Sachs-Wolf effect, while this term psi at the location of the observer has a small effect but very difficult to detect, because it's true that today the gravitational potential at the location of the observer has some value, some non-trivial value, it does not vanish. But because this value does not depend on the direction of observation, this term is the same for the photons that we see from all directions. So we will not be able to measure this term because it will contribute to the average temperature of the photon, and it will change the average temperature of the photon with respect to its true cosmological average value by such a tiny fraction that we can forget it completely. So then the effect is conservative when phi m psi is static and already accounted for with the Sachs-Wolf term. But when phi m psi depend explicitly on time, then the effect is not conservative. There is a net integrated Sachs-Wolf effect. Why? Suppose that the photon crosses a gravitational potential well late, at a time when this gravitational potential well, due to gravitational effect, is getting deeper and deeper with time. Then when the photon enters, it gains energy. But when it's time for the photon to exit the potential well is deeper. So it will lose more energy by going out than it gains energy by getting in. And so there is a net effect that is catched up by the integral. So let me go back to the full formula here. Ah, no, I wanted to go here. Okay, in our full integral, we have an integral over time from decoupling until now on phi psi plus psi prime, and it really captures the integrated effect from decoupling until today. Okay, so these are the three big effects that contribute to CMB anisotropies. Yes? It is all what I'm doing is first order in perturbations, yes, because you never find a square. It's true that you can study CMB at second order in perturbations. This is relevant, especially when you want to understand how the CMB gets lensed. And I will not treat this in the course. I will mention it later, but the first order is complicated enough for a first course on the CMB. So all what we are doing is first order. All right, summary. Our goal was to compute CL, and we see how we are going to estimate the non-trivial part here, the theta L. We are going to estimate it from this integral. But we are not done, because we see that this integral still depends on these functions in red, and we still don't know what these functions look like. But this is our last task before we understand the CLs. So our last task is now to understand what is the dependence of theta 0 on wave number at decoupling, what is the dependence of theta b as a function of wave number, I forgot the comma k is here, at decoupling, and what is the behavior of the metric fluctuations at decoupling, but also at all times after decoupling. Because of the integrated Sachs-Wolf effect, I need to know them at all times after decoupling. And at least we will work in the approximation where psi and phi are the same, because we will neglect the effect of the anisotropic stress. So this is the last task that will bring us to the full understanding of this shape. And we start it now. So, so we need to solve now finally the equations of motion in order to compute these four functions. And the equations of motion are complicated, so as usual in physics, to get a linear some understanding, we will do some approximation. And the clever approximation is to say that instead of considering a very gradual, very progressive decoupling of the photons, we will pretend that the photons are very strongly coupled to electrons and baryons through Thomson scattering until the time of decoupling, and then completely decoupled. And in the regime where they are coupled, we will use this famous approximation, the TCA, tight coupling approximation. So this approximation is obtained when the Thomson scattering rate is much bigger than the Hubble rate. And then so the photons and the baryons should behave as a single fluid because of mutual interaction. And so we expect that a single equation of motion will describe both of them at the same time. So the idea is to look at the individual equation of motion of baryons and photons, take this limit, and derive from them a single equation for the total. And it can be done. It's not very difficult. They are, again, detailed in my notes, as for everything in the lecture here. And the first thing is that in tight coupling, you have a relation between delta gamma and delta B. This is, again, because when we are in thermal equilibrium, the density of photons scales like the temperature to the 4, and the density of baryons like the temperature to the 3. We take logarithmic derivatives. we find that delta gamma is 4 delta t over t. Delta B is 3 delta t over t. We eliminate delta t over t, and we get this equality. And then finally, remember that delta gamma is 4 delta t over t, and we get the first equality. And so the densities of photons and baryons are strongly related. We don't need to follow them independently, and they are captured by the monopole theta 0. We have seen that when Thomson scattering is efficient, it wants to align the baryons and the photons. So theta B and theta gamma remain equal. And we said that the bulk velocity of the photon is captured by the dipole of the temperature anisotropies. And when you do the calculation, you find that they are related up to a factor 3k. And finally, we say that when Thomson scattering is efficient, it wants to isotropize the fluid, and higher multiples vanish. So now you can go back to the equations of motion from yesterday, use all these approximations, combine the equations together, and obtain the famous tight coupling equation, which gives the evolution of the system in this limit. And I'm going to comment on the different terms. If there was no gravity in the problem, we would have only the red terms. Theta 0 prime prime plus k squared cs squared theta 0 equals 0. This is the equation of propagation of sound in a medium without dissipation, telling you that when you generate an overdensity, you have a density wave or a pressure wave propagating up to infinity without losing energy, at least when cs is a constant, the sound speed. So in theta 0, you have delta rho. But in the sound speed square, you have delta p over delta rho. So this product has a delta p. And so k squared times this term is related to the Laplacian of delta p. And this is the usual way to express pressure forces in fluid dynamics. So this is a term that says that we have an oscillator and the mass is given by the sound speed of the oscillator. And so it will feature propagation of sound. We generate fluctuations through inflation, and then these fluctuations propagate like sound waves in the early universe in the tightly coupled photon-baryon fluid. It's as simple as that. What makes the problem non-trivial is gravity. Gravity will enter through different effects. The importance of this effect is proportional to the green level on the slide. So the most important one is this one. Here you find the Laplacian of the gravitational potential. It accounts for gravity forces. You don't need gravity forces to have propagation of sound. But if there is strong gravity in a problem of propagation of sound, it will change the evolution because the gravitational force will be opposed to the pressure force. Pressure force wants the particles to be split apart. Gravitational force wants to concentrate them. So this will play a role. This term is a friction term, and it's related to R. R is the baryon density divided by the photon density, rescaled by a factor 3 over 4. So it tells you what is the weight of the baryons in the baryon photon fluid. When R is big, baryons are important. When R is small, baryons are negligible. Since rho b scales like a to the minus 3, non-relativistic species, and rho gamma like a to the minus 4, relativistic species, this R grows with the scale factor. Baryons are more and more important. Decoupling takes place at the beginning of matter domination when R is significant, is of order 1. When you have more and more baryons, it means that your fluid has more and more inertia, because you cannot neglect that baryons have a mass, and when you have this propagation of acoustic wave, you must move the heavy baryons. There is inertia. This inertia appears in the propagation of sound as a friction term. And so this will be important at late time during radiation domination. The last terms here are the following interpretation. This term is like a local correction to this one. This baryon damping depends on R, but it depends also on the Hubble rate. We have here the average Hubble rate, and here a local modulation of the Hubble rate, because we have 5 prime. So this term is like a correction to this one, coming from what I said 2 days ago, that there is like a local correction to the Hubble expansion rate. And this term comes from the dilation effect that we have already mentioned before. The sound speed has to be computed from delta p over delta rho summed over baryons and photons. If we had only photons in the fluid, CS square would be 1/3, because for a relativistic fluid, P is 1/3 of rho. And so delta P is also 1/3 of delta rho. However, CS square is delta P plus of the photons plus the baryons divided by delta rho of the photons plus the baryons. And the baryons make a difference because they contribute to the density but not to the pressure. So when you do the calculation, you find that this coefficient R appears in the sound speed. At early times during radiation domination, the baryons are negligible. We have our 1/3. At late time, close to decoupling, R is big, the sound speed drops. When you have a drop in the sound speed in this equation, it means the propagation of the wave slows down and gets damped. And you can see this when you look for analytic approximation to this equation. So if you like analytic approximation to CMB physics, the gold mine is the thesis of Wenyu and all the papers written by Wenyu and Sugiyama. They are full of beautiful analytical approximations to such kind of equations at different levels of precision. To discuss this equation, let's forget these terms. These terms are not too important. Let's also forget the friction term for a while and consider the dominant terms. This is the equation of a harmonic oscillator. The oscillation takes place around an average value. How do you find the average value? You find the average value by setting for a while the derivative to 0, and it gives you the equilibrium solution. And the equilibrium solution comes from just this equality that you can recast as theta 0 equilibrium, meaning 0 point of the oscillation, equal to -1 plus R psi. So if we don't have a gravitational force, then this is 0. The oscillations are symmetric around 0. It means that our sound wave have a symmetry between compression and rarefaction. When the sound propagates, compared to the average density in the universe, you have compression zone, rarefaction zone that are traveling at the speed of sound, and they are symmetric with respect to the average density. Because of gravity and the existence of a gravitational potential, the gravitational forces break the balance because they want compression. They are always fighting for compression. So the compressed zones are more compressed than the rarefaction zones are rare. And so you shift the 0 point of the oscillations. If the baryon density is important, this effect is enhanced because gravity plays even more role. This will be the key at the end to understand why we measure omega b so well with the CMB. You will see that this is fun. It comes directly from this equation. Finally, still neglecting these terms, looking at these ones, it was shown, I think by Wenyu, maybe by somebody before, but I know it from Wenyu's work, that this has an analytic approximation given by the first order WKB approximation method. And the solution looks like this, and it has oscillations. The argument of the cosine is Kc integral of Cs d eta. So for instance, during radiation domination, when Cs is a constant, you get Kcs eta. So it shows how these acoustic waves propagate. When in real space you have propagation of a plane wave, the Fourier transform exhibit oscillations. So these oscillations are the Fourier description of the propagation of the waves. There is an amplitude here, which is given by a constant of integration modulated by this 1 plus R, showing that when the baryons matter, because of their inertia, the amplitude of the oscillation gets damped. R grows, so 1 minus R to the power minus 1/4 decreases. And this correction accounts for the 0 point of oscillation that make the solution asymmetric with respect to 0. This is a very good approximation to theta 0, just neglecting two things. It neglects the fact that there are these dilation and gravitational corrections. We will see what role this has. And it comes from the tight coupling approximation. So it neglects the fact that when you approach recombination, this equation is not a good description anymore. And then to understand what happens, you have to remember what we said about the diffusion length. The diffusion length is a length over which photons travel between the early universe and a given time. When the scale approaches the diffusion length, the fluctuations get washed out because this diffusion process redistributes completely the photons and averages any anisotropy within a radius given by the diffusion length. And this is not captured by this equation. If we wanted to capture it, we could use this diffusion length and multiply all this solution by an exponential of minus the scale divided by the scale of the diffusion length to account for this additional damping of the fluctuations when we exit the tight coupling regime. Yes, sure. What is, sorry? The lower index here. This is a monopole. So we have expanded our theta in multiples. And I remind you, we said monopole equal local density. Dipole equal bulk velocity. Quadrupole equal anisotropic stress. And then we have all the higher multiples. And the beauty of, one of the beauties in the formal solution of Zaldariaga is that in order to estimate any multiple L, you only need to know the monopole, which is here, and the dipole, which is here. And all the higher values of L are then trivially obtained by geometrical projection effect captured by the Bessel function. So because in this formula, the most important term is theta 0, we are concentrating on theta 0, and this tight coupling approximation gives us an equation of motion for theta 0. Good. Now we are going to look at the typical evolution of one mode with a given wave number k. So it means that in all the next plots, in our vertical axis, we will have transfer functions. You remember transfer function depend on time and k, but we have fixed k. I've used a given value here. Later we will see what happens for other values. And this is time growing from some time before photon decoupling until today. We have characteristic time. There is a time of recombination, which is here, meaning that today would be further on the right. I've cut the diagram. This is a time of recombination. This is a time of equality between matter and radiation, which is a little bit before. I can define a time of crossing of the sound scale, but I will leave this out for this discussion. But for each mode, you have a time of Hubble crossing, the time at which the mode enters into the Hubble radius, when k is of the order of AH, or k eta is of order 1. And of course, this time depends on the value of k. You have modes that enter the Hubble radius during radiation domination, and then the red line is before the black line. You have modes entering during matter domination, and then the red line is on the right of the black line. And I've chosen here a mode crossing during radiation domination. So the red line is on the left, is here. All right. And first, I start by showing you the behavior of the metric fluctuation psi. It's a transfer function that I want to plot. I want to plot the transfer function of psi normalized to r equal 1. This is our convention for transfer function. If you go back to the adiabatic initial condition, you find that then psi must be 2/3. This is completely arbitrary. We could do everything normalizing r to -3 and compensating by our definition of the power spectrum. It's arbitrary. So we stick to the usual convention. We start from 2/3. We have 0 here, and we see that when the mode approaches the Hubble scales, it decays to 0. So metric fluctuations decay when they approach the Hubble radius during radiation domination. Is it obvious? No, not obvious. You show it with the Einstein equations, of course, and in particular, once you are inside the Hubble radius, you can use the Poisson limit of the Einstein equation. So for simplicity, let's look only at the Poisson equation. The Poisson equation relates the Laplacian of phi to the density, the total energy density in the universe. In this first line, I am considering what happens during radiation domination. So I have the fluctuation of radiation, because matter is still negligible. The overall trend that is described by the Poisson equation is that because the universe expands, it is trying to iron out metric fluctuations. Just because everything is stretched, phi tends to go to 0. Except it, either when we are on super Hubble scales, and then for, we have seen that on super Hubble scales, the adiabatic initial condition, which solves the Einstein equation, says phi is constant. So phi is protected from decay when it's on super Hubble scales. Probably has to do something with causality, but let's not enter into these details. The other situation in phi will not decay is when there is gravitational clustering, because gravitational clustering wants, on the contrary, to create more density contrast and so deepen potential wells. During radiation domination, when you enter the Hubble radius, gravitational clustering is not important, because during radiation domination, the dominant fluid in the universe has pressure. Pressure is then more efficient than gravity and prevents significant gravitational clustering of the total matter. So in my Poisson equation, I replace delta rho r by the rho r of the background times the relative fluctuations. I remember that rho r scales like a to the minus 4, and I find that phi evolves like a to the 2, which comes from the Laplacian, but we moved it to the right. A to the 2 minus 4 because of this rho r. And since delta r, which is the density contrast of radiation, does not increase with time, okay, because simply I don't have efficient gravitational clustering, I consider it as constant. In fact, it's oscillating, but on average, it's constant. So we sum up the powers, we get a to the minus 2, and we find that the ironing of phi is the most efficient effect, and phi decays. So it goes to 0. This will be important. If our mode, I anticipate on what we will find later, if our mode would cross the Hubble radius later during matter domination, to see what happens, I will need to look at the Poisson equation during matter domination, not with a delta rho r, but with a delta rho m. I would then have on the right-hand side scale factor square, rho m, which dilutes like a to the minus 3, and delta m. And as Ruggiero said yesterday, when you look at the equations of motion of matter during matter domination, you find that density contrast grow proportionally to the scale factor in the linear regime. And this describes the gravitational clustering of matter. So I have a power 1, and by magic, the powers cancel out, and we find that phi remains constant on sub-Hubble scales during matter domination, as if the ironing from expansion of the universe and gravitational clustering from gravitational forces would exactly compensate each other. That's a remarkable result that will be useful later, and I think at some point also in Mustafa's course. Okay, so we have described the transfer function of psi. That's the first step, but we have a list of functions to study, and the next one is phi, the other metric fluctuation. It's essentially the same. There is a small difference because here I'm doing no approximation. I'm taking the full class solution. Small difference comes from anisotropic stress of the neutrinos. We neglect it. Then, having this, I will plot in dotted line what I expect to be the 0 point of the photon acoustic oscillation. We said it's minus 1 plus r psi. So I take this function, I multiply by minus 1 plus r, and I get a symmetric, almost a symmetric function with respect to 0. And then we can plot the evolution of theta 0. We look what is the initial value of the transfer function for theta 0. We go back to our initial conditions. We find it with our normalization, it should start from minus 1/3 here. After that, what do we expect? We expect that to see oscillations, the acoustic oscillations corresponding to the propagation of acoustic waves, and we expect that the oscillation take place around the 0 point. So we expect something like this, boom, and going up and ending up like this. And the solution looks a bit more complicated. But yeah, it is still oscillation centered on the dotted line, right? If you try to catch the inflection points coincide pretty well with the dotted line. What is a bit funny is that the amplitude seems to change. The amplitude here is this distance. And then you would expect the next oscillation to have the same amplitude, but it has a bigger one. And then if I report this amplitude here, I find that the amplitude has increased again. But later on, the amplitude decreases. We can understand all this. There is here a phase where the amplitude increases. Why? Because it is a phase in which phi and psi have a time derivative. They vary. If they vary, we go back to our tight coupling equation. If they vary, these terms are non-zero. And they are like a term injecting energy in our harmonic oscillator equation. This is called the gravity boost. When metric fluctuations are non-static, they inject energy in the oscillator. The deep reason is that there is this local baryon damping and this dilation, but the dilation wins and it injects energy into the system in such a way that the amplitude of the oscillation here is growing. Until psi and phi stabilize, then forget about the gravitational boost. It will not contribute anymore, and for a while we see that we indeed have some nearly stationary oscillation with a constant amplitude. But at some point the oscillations are damped again. They are damped for two reasons. First, they are damped slowly because in our WKB approximation there was a 1 plus r to the power minus 4. It accounts for the fact that the sound speed of the fluid decreases during matter domination. And then there is exponential damping. Exponential damping is a fact, comes from the fact that we are leaving the tight coupling approximation. The scale that we are considering, it becomes comparable to the diffusion damping scale from Monday. And so diffusion damping erases everything within a radius of lambda d, and this means that this mode then will be exponentially damped. And this mode is not interesting anymore for CMB physics because at the time of decoupling, we have completely washed out theta 0. We will see that this mode contributes to the tail of the CMB spectrum. So smaller modes would be more interesting, smaller k, because they did not decay completely at the time of decoupling. Before I move to the other modes, we are missing something. We say that to understand our line of sight integral, we need theta b, the velocity of the baryons. The velocity of the baryons is related to the monopole theta 1. Density and velocity, you know, in a harmonic oscillator, they are having the same kind of evolution, but with a phase shift. Here it's the same. The monopole and theta b, or the monopole and the dipole, have qualitatively the same oscillation, but with a phase shift. And so if we plot theta b, we get oscillations. Sorry, I wanted to go to the next one. Yeah, we get not yet. Okay, so I will change the order. When we plot theta b, we get some oscillations in green, but they are out of phase with the blue one that we had described. There is an out phasing here. And this will be not too important, but this will play a role later. Now let me go backwards. We were here. We have understood metric fluctuation. We have understood theta 0. But we remember that what matters for the CMB is the intrinsic fluctuation corrected by the Sachs-Wolf term. So it is actually this sum which is important. And to get the sum, I need to consider 2 times the average between the blue curve and the yellow curve. So let us plot the average because it's very intuitive. And then if we multiply it by 2, it gives this sum. So the average is here. It starts between the yellow and the blue. It starts to oscillate like the theta 0. And then at some point, theta 0 plus psi becomes identical to theta 0 because the metric has decayed. So the light blue curve, which is corrected by the Sachs-Wolf effect, looks qualitatively similar to the dark blue curve, which is theta 0, except that the first oscillation look a bit different. And for instance, you see that this curve is crossing 0 here, while theta 0 is not. The crossing of 0 can be identified later as a pattern in the CMB spectrum. Okay, so we have understood this term. We have understood the Doppler term. We leave the integrated Sachs-Wolf for later on. Now that we have understood the evolution of one mode, let's look at all modes collectively. And the best then is to use this kind of 2D plots with colors. On these plots now, the time is flowing from the early universe in the top to the late universe at the bottom. And here I have my wave number from small k to large k, meaning from small wavelengths to large wavelengths. The red line is a line corresponding to Hubble crossing. When you are below the line, you are on sub-Hubble scales. Above, you are on super-Hubble scales. And we explained that the scales we see today are by definition sub-Hubble. So we see scales which are below the red line. But we show also explicitly that if we go back in time, our modes will become super-Hubble one after each other. And indeed, we see that at the beginning of this plot, the modes that we observe here were super-Hubble. But they cross the Hubble radius one after each other. Now we look at the time corresponding to equality between radiation and matter, and the time corresponding to recombination. And we find that these different lines separate different regions in which there will be different phenomena and analytic approximations, which are the key to understand the details of CMB physics. But now we will speed up a bit. I will not tell you about all details. What is very interesting is this crossing. This crossing tells you that there exists a scale in the middle of the observable range, and this is the answer to the questions of one of you before. There is a scale in the middle here, which crosses the Hubble scale at recombination. What we observe with the Sachs-Wolf term are fluctuations at recombination. The one coming from the large scales were then still super-Hubble. The one coming from the small scales were still sub-Hubble. And so what I call large or small scale is usually defined with respect to this characteristic scale. The yellow line corresponds to sound horizon crossing. I won't enter into the details of comparing the red and the yellow. Let's stick to Hubble crossing. It's enough. Now, the color levels in this plot stand for the value of the metric fluctuation phi, and the value of psi is essentially the same. The color code is here. Red is positive, blue is negative. This is always for the transfer function normalized to r equal 1. And we see that on super-Hubble scale, we have a homogeneous dark blue color, which corresponds to the value of 2/3. These are where the adiabatic initial conditions are taken. We see now explicitly that if I look at a given mode, a given k, it means I draw a vertical line, and the evolution is along this line. When the mode crosses the Hubble radius during radiation domination, the fluctuation gets damped, and it goes to 0. The dark blue is not negative, it's just 0. This fluctuation of the metrics, they never become negative if you have normalized them to r equal 1. So the fluctuations get damped. While if the fluctuation crosses deep into matter domination, doesn't get damped. It remains essentially constant. There is no gradient of color along vertical lines because phi remains constant during matter domination. You could show that phi ultimately decays or starts to decay during lambda domination. The limit between matter and lambda domination is this black line. It's a bit before today. The bottom is really today. And if we would zoom here, we would see a gradient of color, but it's very hard to see by eye. It's becoming lighter here because there is a bit of decay of the metric fluctuation during lambda domination. This is a very well-known consequence of the Poisson equation during lambda domination. There is an intermediate region here. There are these modes that cross the Hubble radius around recombination. Then you are during matter domination, but radiation is still significant. So there is still a little bit of a gradient, a little bit of variation of phi along vertical lines. This will be important later. So this is qualitatively the evolution of the metric phi for all modes. Now this was just to support my discussion and highlight the trends, but I already explained this. The fact that here there is a very clear time derivative of phi, so the color changes very quickly when time evolves, means that this region is an important region for the gravity boost. This is where the amplitude of the acoustic oscillations get amplified. The fact that here the metric fluctuations are not stabilized means that there will be an early integrated Sachs-Wolfe effect here. The integrated Sachs-Wolfe effect, by definition, can only take place after recombination. But it can only take place when I have a partial derivative which is non-zero, which means that when I go down, the color changes. It's still a little bit true on these scales around Hubble crossing after recombination, because we are not deep in the matter-dominated era. So you see that here I still go a bit from red to blue. And so the variation of the metric here at the end will be responsible for a Sachs-Wolfe effect that we will call the early Sachs-Wolfe effect. And also here, if we would zoom, we would see the metric decay. And so this region will be responsible for a late integrated Sachs-Wolfe effect. But deep during matter domination, there will be no integrated Sachs-Wolfe effect, because deep during matter domination, the metric is totally static. We are fortunate, we are lucky to be in this situation, because if phi and psi were not static during matter domination, they would constantly change the temperature of the photons, and they could even erase the primordial information. This is not the case. During the long matter-dominated era, there is no integrated Sachs-Wolfe effect, because fortunately the metric fluctuations are static. This is why the CMB map is still mainly about what happens at decoupling and not about photons traveling through clusters. All right, same exercise with the other super important variable, which is a monopole, theta 0, which is a variable in the tight coupling approximation. We normalized it to a value of, I think it was -1/3 here. And so we have a homogeneous -1/3. So here blue is negative and red is positive. We always have the same lines, Hubble crossing, equality, recombination. And we see that at the approach of sound horizon crossing, we go through blue, red, blue, red, blue, red. These are the acoustic oscillations. And when the modes have a larger case, smaller wavelengths, they enter very early and they have time to go through many oscillations. When the modes enter into the Hubble radius just before recombination, they don't have time. They have time just for maybe one period or half a period of oscillation. But then what we see in the CMB, because of the first term in the line of sight integral, is a picture of this fluctuation at recombination. And so if we look at very large scales, very small scale, we see them on the super Hubble regime. They just reflect the boring initial conditions. They are constant. Then we will start to see modes that have been amplified by gravitational boost, or that could oscillate by half a period, 1 full period, 1.5, 2, 2.5, 3, 3.5, and this will give us a series of acoustic peaks. The acoustic peak comes from the fact that we catch a mode at a given phase of oscillation, of its oscillation. And the oscillation described in Fourier space the propagation of the waves in real space. And the last interesting thing in this plot is that we have the diffusion damping scale, which is materialized in blue. The blue line, to be precise, is a line on which a given mode crosses the damping scale defined on Monday. The damping scale increases with time, so in Fourier space it's decreasing. And it would go in principle to infinite scales, meaning k goes to 0. And we see that when a mode crosses a damping scale, the fluctuation gets exponentially damped, just washed out, averaged, due to the complicated diffusion effects. And so we don't expect to see all the peaks. We expect that at some point the peaks fade away and there is nothing left to observe. This effect is called silk damping and explains the exponential tail in the CMB spectrum that we will derive. Okay, so to recap, what we will observe at the end is mainly theta 0 at recombination. So we will observe a cut across this line. These lines look parallel and symmetric. It's because during radiation domination, the argument of the cosine is kcs eta with a constant cs. So because you have a k eta and because we use log scale, you have parallel lines with an angle of 45 degrees, meaning that if I do a cut along a horizontal or vertical line, I see the same oscillation patterns. And, okay, I already said this. If I look at the evolution of a mode at a given scale, I see the oscillations. But on the contrary, if I look at all modes at a given time, I see roughly the same oscillations. And this is why I can go now to a plot like this. It looks a bit like the previous plots. That's because of this symmetry and this angle of 45 degrees. But this plot has a completely different goal. Because in this plot, instead of choosing a mode and showing here the time evolution, we do a horizontal cut. We choose the time of decoupling. This should be eta dec, not tau dec. We choose the time of decoupling, and we plot the transfer function as a function of k. So we are doing now a horizontal cut through the previous surface. But we understand the shape of all the curves now. We have, again, for the metric fluctuation, a constant value for super Hubble scales, and then the curve goes to 0 because during radiation domination, these modes have been erased when crossing the Hubble radius. So the curve goes down. Using the metric fluctuation, we can plot the 0 point of oscillation as dotted line like before. And then if we take a picture of theta 0 as a function of k at decoupling, we have qualitatively the same curve as before, again, with this constant value on super Hubble scales, and then this series of oscillation, roughly centered on the dotted line, and with an amplitude that has been increased compared to this for modes that cross during radiation domination due to this gravitational boost effect. The blue line, the light blue line, which accounts for the Sachs-Wolf effect, is again the average between the yellow and the dark blue. It has these patterns with points crossing 0. And we clearly see that the minima are deeper than the maxima because the curve is centered on the dotted line and not on 0. So there is an asymmetry in the oscillations here. And finally, theta b is taking into account this velocity of the fluid and has oscillation, but the oscillations are out of phase. And theta b is negligible for super Hubble scales because super Hubble scales are static. They are static. There are no significant bulk velocity. Theta b is 0 on super Hubble scales. This plot brings us very close to understanding the CMB spectrum, as we shall see. What we would like to do is now to go from a representation in Fourier space to a representation in multiple space. But we said that, at least for the Sachs-Wolf and Doppler effect, there is a one-to-one correspondence between the value of k and the value of L. So from this plot, we should be able to guess the shape of the CLs. And this is what we will do now by superimposing several curves, several plots. This is the same plot as in the previous slide. It shows transfer functions. Now remember that in the CLs, we have an integral over the square of the transfer function. So let's square this plot. We square it. I'm so far only interested in the Sachs-Wolf contribution, so I square the light blue curve. And I get this pattern with a plateau, and I reach 0, and then I have my first peak, second peak, third peak, etc. I notice that the first and third peak are bigger than the second and fourth peak. This is just because I'm squaring with respect to 0, and because this dotted line was introducing an asymmetry between maxima and minima. So when I take the square, I see that this square is big, this square is small, this one is big, this one is small. So the asymmetry ends up in creating an asymmetry in the squares. And I see that at some point, my peaks have an exponential envelope and the exponential envelope comes from this diffusion damping. And now, in principle, I could imagine that if really a given mode K corresponds to a CL at a given L, if I adjust a K scale to an L scale and I plot the CLs below, the CLs will look like this curve. This would be true at least if there was only the Sachs-Wolf effect. So what I'm going to plot here is not the full CMB spectrum, but it's what you get when you ask a Boltzmann code to plot the CMB spectrum taking only the Sachs-Wolf term into account. And you get this. This is plotted now. This is a CL as a function of L, of multiples. But we have rescaled L by eta 0 minus eta rec. I have some tau values here. I should change them in eta, because in this lecture, I always call conformal time eta. So I rescale my L in order to have automatically the correspondence between L and K that we have described, and that comes from the spherical Bessel function. And we see that the blue curve here, which is a contribution of the Sachs-Wolf term to the CL, actually looks like the square of the transfer function. So we will comment on the similarities and the difference. First, why do we have a similarity? It's because the CLs are supposed to come from an integral over K of the transfer function squared times the primordial spectrum. Here I took a scale invariant primordial spectrum. Suppose that I take a scale invariant primordial spectrum. I will go back. I will show again the formula for the CLs. Is it here? No, it's not here, so I go backward. I go back to the first slide with the CL. It was a few slides ago. Here. Suppose that your primordial spectrum is constant. Very good. So it does not depend on K. And suppose that this transfer function would be constant. We have seen that it's constant on super Hubble scales. But for a while, let's imagine that it's always constant. It's a line. And suppose that we take... what I meant was, suppose that I only take the Sachs-Wolf effect. So I only have this contribution to theta L. And theta 0 plus psi is constant. It's horizontal. Then this is just a number. Then I put this expression in here. This expression is still non-trivial because there is a spherical Bessel function. But if this is constant and this is constant, you can do this integral analytically. It's an integral over the square of a spherical Bessel function. It's very easy to do it analytically. And you find that CL is 1 over LL plus 1. So if the transfer function was trivial and the primordial spectrum was trivial, the combination LL plus 1 CL would be a constant. And this is exactly the reason for which, by convention, people always put as a vertical axis of a CL plot, LL plus 1 CL. And here I have LL plus 1 CL. So if this transfer function was constant, the CL would be constant. Is it the case? The transfer functions are constant on super Hubble scales. So they contribute to a constant LL plus 1 CL on small l, and this is called the Sachs-Wolf plateau. And here you directly see the pattern generated by inflation, because the transfer function is trivial, so you directly see your primordial spectrum. This is horizontal because inflation generates a nearly scale invariant spectrum. But the complicated physics of acoustic oscillation modulates the initial horizontal line. The initial condition would like a horizontal line. It gets modulated by the acoustic oscillations. And so LL plus 1 CL, instead of being constant, gets modulated. So what you get here is a prediction of inflation, which is a flat line, modulated by the minima and maxima of the acoustic oscillation. So this is why we have Sachs-Wolf plateau acoustic oscillation. And then you see that the patterns look the same. We have large peak, small peak, large peak, small peak. Why? Because we are really relying on this curve, and the 0 point of oscillation has created this asymmetry between large and small peak. We have the exponential damping, but the shape is a bit different. Instead of going to 0, we don't reach 0. And our peaks, they are not as big, and they are wider on the lower plot. As if the lower plot was a smoothed version of this plot. And I have time to explain the smoothing, and then it will be a very good time to stop. So when I go from the square of the transfer function to the CL, why do I have a smoothing effect? It's because decoupling is not instantaneous. I have non-trivial projection effects coming from the thickness of the last scattering surface. Decoupling is not instantaneous, so when I see a photon, it's not coming from exactly from a point, which is the intersection of the line of sight with the last scattering sphere. It's coming from a region, and this region is a region from where the photon could originate. But the photon, before its last interaction, had a non-zero mean free path. It could have originated from anywhere in this circle, and after its last interaction, it could travel in straight line to me. So when I look at a given line of sight, I'm not probing a particular value in the universe from where the photon has been emitted. I'm probing a small finite region. And this finite region then leads to a smoothing of fluctuations. The smoothing is both in angular space and along the line of sight, because this region has an angular diameter and a depth. And these two effects are accounted mathematically by our line of sight integral. By the fact that this is not a Dirac delta function, it's a function with an extension in time. So in your integral, you have a smoothing because you integrate over several times, close to recombination. And then the angular smoothing is accounted by the Bessel function, which is not a Dirac delta function either, but which is given by peaks with a width. And so these two effects tend to implement a smoothing, and this is why here we don't reach zero and our peaks are smooth. This is a very good time to stop. We have been quite far. We have almost our final answer for the CLs. The only thing is that we have only taken into account the Sachs-Wolf term. What we will do tomorrow is add Doppler and the early integrated Sachs-Wolf, and we will have the final shape of the CL. We will comment it a bit. We will explain why it depends on the cosmological parameters, and so why this function is actually a Rosetta Stone. And we will comment a bit on the fact that there is also CMB polarization, and on the fact that we have only spoken about scalars, but tensors also could play a role in this picture. This is a program for tomorrow. And the program of Friday is what do we learn from observations? Thank you.
Given the time that the potential are constant, and the fact that there is no variation, there is a compensation in the redshift and blueshift of photons while they go through the potential, assuming that the potential is spherical or has some symmetry, right?
So the question is, I go back to this kind of plot, and we said here the metric during matter domination, the metric is static. So the integrated Sachs-Wolf in this regime is conservative, and we can forget about gravitational potential waves during matter domination. This is exact in linear perturbation theory, which is sufficient here. There is absolutely no assumption of any symmetry of the gravitational potential waves. Phi m psi, the metric fluctuation can be an arbitrary complicated function of time and space, not of time, of space. In real space, in Fourier space, they can be very complicated. They don't necessarily have any symmetry or spherical symmetry. They are static. If they are static, the effect is conservative and they don't leave an imprint. So no, this is a very robust prediction that the metric fluctuation during matter domination are irrelevant for CMB physics. What matters are only the metric fluctuation at very late time because they decay during lambda domination, and at very early times because recombination takes place not so far from radiation domination when the metric has not stabilized. In between, the effect cancels exactly in linear perturbation theory. You could have non-trivial effect in nonlinear perturbation theory, but the modes that we contemplate here, which are relevant for CMB physics, they are very deep in the linear regime. Non-linearities happen on very small scales at those times, which are not relevant for CMB physics. And so you can completely rely on this. That being said, the fact that phi m psi is constant is model dependent. If you start to play with modified gravity models like F of R theories, these could change. You could have a non-trivial evolution of phi m psi during matter domination. Also, the fact that our universe contains massive neutrinos can become non-relativistic at redshift of 10 or 20 or something like this. And they are not perfect cold dark matter. They don't have the same growth rate as cold dark matter, so they can introduce a very small variation of phi m psi. So phi m psi are exactly irrelevant in lambda CDM, but not necessarily in extensions of lambda CDM. But this is really related to the equations of gravity and the content of the universe, and not to an assumption of sphericity or something like this. This is not relevant.
Delay interprets as well related to the structure formation.
It's a combination of two things. It's a combination of the fact that since you have structure formation, phi m psi have a non-trivial evolution, but this non-trivial evolution is revealed by the fact that the background evolution is given by lambda domination. So here structures are also forming, but we are on linear scales. So they form in such a way that the density contrast increases while the metric fluctuation is completely constant. Okay, so the two are not contradicting each other, which is counterintuitive the first time you hear about it. But the Poisson equation gives a relation between phi and delta with scale factors in the middle. So you can have delta growing due to linear structure formation and phi constant. It's a kind of miracle that on linear scale, structure formation takes place with a static potential. During lambda domination, structure formation requires the metric fluctuation to vary, and it reveals the fact that there is an integrated Sachs-Wolf effect. Okay, so the modes are frozen here, but they start evolving when they approach the Hubble radius. So it's not the case that exactly when you cross the Hubble radius, you become causal. It's a progressive effect. So only when they approach the Hubble radius, they can start to evolve. Before they are frozen. Yeah. Also, this thing of being frozen or not is not as deep as you think. It's a gauge-dependent statement. I could do this lecture in another gauge, the synchronous gauge, and then everything would always be evolving. Evolving or not doesn't mean being causal or not causal. It's more complicated. But it happens that Newtonian gauge is very intuitive because it shows frozen quantities well before Hubble crossing.
Okay, we can go in for a coffee and we will reconvene at 11.